Hi everyone, this is the video report of Science 2 Assignment 1. I am Gaurav Batra. Basically in this assignment we had three questions. The question 1 is that we have to plot the average number of particles in a given energy state versus the energy state minus alpha where alpha is minus beta mu where mu is the chemical potential. We have to do this for different distributions like Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac. We had to analyze the results at low temperature, intermediate temperature, and high temperatures and T equal to 0. So let's start with Maxwell-Boltzmann distribution. As done in class, we know that the dependency of the average number of particles in a given energy state is given by the formula on the energy levels given by the formula. We can simplify this formula further to get an exponential graph with the equation of y equal to e power minus x by kt, where k is a constant. So we observe these different graphs for different t's. At low t, we have at low t, high t, intermediate t, and t equal to 0. This is a visual representation of the same thing. We see that as a few observations are that as we increase the temperature, the line almost becomes horizontal to the x-axis. At low temperature, most of the particles are very little speed, so the graph drops very sharply. At t equal to 0, the graph becomes vertical as there is no energy in the system and the speed is 0. At intermediate temperatures, we get a very smooth exponential graph. At high temperature, the line is almost vertical to the x-axis. Now we'll move on to the Bose-Einstein distribution. The Bose-Einstein distribution is given by this formula, which can be further simplified to get y equation of the form y equal to 1 by e power x by kt minus 1. We observe one thing that at x equal to 0, this term goes to infinity. So we get a graph like this at low temperature, high temperature, intermediate temperature, and for t equal to 0. A few observations, a visual representation of the following is given by this. A few observations are that at t equal to 0, we get a graph which is almost same as the previous graph, as the energy in the system is 0 and speed of the particles is 0. At low temperatures, we get a graph which has a very high slope and goes off to 0 very quickly. As we increase the temperature, the decrease in values of the graph reduces and we get a more smooth exponential graph. Now we'll move on to the Fermi-Dirac distribution. The Fermi-Dirac distribution is given by the formula given on the screen. The only difference between Bose-Einstein and Fermi-Dirac formulas is that instead of a minus 1, we have plus 1 here. But this contributes to a huge difference in the shape of the graph. We see that the different types of graph at low temperature, high temperature, intermediate temperature, and t equal to 0. One thing we observe that at t equal to 0, we get the same graph in all the three cases, and at low temperatures we get a graph which falls off very rapidly. Where in a few energy states, the average value of particles decreases to 0, and as we increase the temperature, the graph almost starts to become horizontal, and t equal to infinity, the graph becomes a vertical line parallel to the x-axis. So the second question is that we have to state the application of Fermi-Dirac statistics. One can apply Fermi-Dirac distribution to any system of fermions and equilibrium and predict the macroscopic properties of a system. Some applications of the Fermi-Dirac statistics are modeling the metals as a gas of electrons. We can model metals as a cloud of negatively charged electrons in a positively charged background. Since electrons are fermions, it's a natural settings for us to use Fermi-Dirac statistics to get information about the system. One interesting observation that we get from this is the Pauli pressure. We observe that there is a non-zero pressure that is exerted as a consequence of Pauli exclusion principle, and this is a direct consequence of the fact that we use Fermi-Dirac statistics to model the system. And the second application is that of the white dwarfs. One of the first application of Fermi-Dirac statistics was in astrophysics, where Fowler applied it to the studies something called white dwarfs. He proposed that we may view white dwarfs as a gas of electrons and nuclei. The pressure exerted by the fermions due to the Pauli exclusion principle, similar to the previous examples of metals, will halt the gravitational collapse of a star if its mass is below a certain level called the Chandrasekhar limit. If the mass of the star is below this threshold, then the collapse is stopped as the fermionic pressure is greater than the inward pull of gravity. But if the mass of the star exceeds this limit, then the star collapses to either form a black hole or a neutron star as the inward gravitational pull exceeds the outward pressure. We can also model nuclear phenomena using Fermi-Dirac statistics. Other applications include Fermi gas model to calculate the binding energy of nucleons in the nucleus. Pauli also explained weak temperature dependence of paramagnetic susceptibility of metals exposed to weak magnetic field by applying Fermi-Dirac statistics to the conduction of electrons. Thank you. In the third question, we have to write a small report on Bose-Einstein condensate, explaining what is Bose-Einstein condensate, how do we condense bosons, and its various real-life applications. A Bose-Einstein condensate is a state of matter that occurs when extremely low density gas are cooled to near zero temperatures. Since multiple bosons are allowed to occupy the same energy state upon cooling, all the particles occupy the lowest quantum states. In such an ensemble, the microscopic quantum phenomena such as wave function, interference, etc., become apparent macroscopically. Bosons are particles that are distinguishable from each other. Now consider a system of two particles in two energy states. If we were if they were classical particles, there were to be four possible configurations. But if the particles were are bosons, they would be indistinguishable, and there would be three possible energy configuration, four possible configurations. Thus, the probability that they are in the same state would be more than the probability that they are in different state. So we conclude that in general, bosons tend to be in the same state that is they are more likely to be found in a same state. Now consider a gas or molecules with the same total energy. As temperature is lowered, the energy of the system is lowered. The desire of the particles to stay in the same state starts to dominate. Thus, at some point, it so happens that a large fraction of particles ends in the smallest possible energy state. This is called Bose-Einstein condensate, where the condensed particles behave like a single quantum entity. So how do we condense boson? The first stage in the condensation is achieved by laser beams propagating in different directions. Their frequencies are tuned such that so that the natural frequency of the atoms. As an atom moves in any direction, the Doppler effect shifts the frequency of an oppositely directed beam upwards so that it has a greater probability of colliding with the atom and slowing it down. The next stage in further cooling is done by evaporation. The trap for the electron uses specially designed magnetic fields as well as careful control of magnetic movements of the atoms to keep them antiparallel to the field. Under these conditions, atoms are repelled by the magnetic force from the strong magnetic fields, which act as walls. Thus, the atoms are energy of thus the atoms are cooled to very low temperatures. Some applications of Bose-Einstein condensate are Bose-Einstein condensate is used in basically development of quantum computers in quantum information processing. It is used to build precise measurement tools that utilize Bose-Einstein condensates and their experimental setups. Some models of dark matter interaction follow Bose-Einstein condensate framework. Uh, Sikbi and Q Yang showed that cold dark matter axions form a Bose-Einstein condensate by thermalization because of gravitational self-interactions. The optical lattices that can be easily modified by varying the interspatial spacing are also developed using Bose-Einstein condensate. Thank you.